Hello everyone, myself Alok Kumar. I am Assistant Professor in Government College of Engineering, Dharmapuri. So here we will see remaining topics of third unit of compiler design. So that we will see here what is the role of intermediate representation and what are the commonly used ways for intermediate representation. That we will see here one by one, and with the help of examples we will see. So here we can see intermediate code generation. So here we already know this one is source program, and at last we are getting target machine code. Okay, so these are the phases that comes in front end, and these are the phases that come in back end. So intermediate code optimizer and target code generator. So in between this intermediate code generator is there. So this intermediate code generator works as a glue between front end and back end. Okay, so whatever abstract syntax tree we are getting, this one work as input for this phase, and we are getting here non-optimized intermediate code. Okay, so here we can see this one intermediate codes are machine independent codes, but they are close to machine instructions. The given program in a source language is converted to an equivalent program in an intermediate language by the intermediate code generator. Intermediate language can be many different languages, and the designer of the compiler decides this intermediate language. So here we can see what are the different roles of intermediate representation. It acts as a glue between the front end and the back end. To lower abstraction from source level. Okay, that is also a role of intermediate representation. To break the difficult problem of translation into simpler, more manageable pieces, to perform machine independent optimizations. Okay, so now here we will see what are the commonly used intermediate code representation. First one is syntax tree. In that we will see directed acyclic graph also, postfix notation, 3 address code, that is quadruples, triples and indirect triples also we will see with the help of examples. So firstly we will see that is syntax tree. It is a condensed form of a parse tree. In syntax tree, the internal nodes are operators and child nodes are operands. To form syntax tree, put parentheses in the expression. This way, it's easy to recognize which operand should come first. Okay, so here we can see with the help of one example. Suppose we are having this SDD, and here these production rule having with the semantic rules we are having, and we can construct the parse tree. From this parse tree we can construct this syntax tree for the expression a minus 4 plus c. Suppose we are constructing this parse tree from this SDD. So here E is generating E plus T, and E is generating E minus T, and after that this E is generating T is generating this ID. Okay, after that this T is generating num, and this T is generating ID. Okay, so like this manner, here whatever operators are there that we will keep at intermediate node, internal nodes, and here the operands we will keep at leaf node. So for this expression a minus 4 plus c, this one is the syntax tree. Okay, so now here we will see directed acyclic graph. So in node n, we can say root node in a directed acyclic graph has more than one parent if n represent a common sub-expression. In a syntax tree, the tree for the common sub-expression would be replicated as many times as the sub-expression appears in the original expression. Okay, suppose we are having one expression like this manner, a plus a into b minus c plus b minus c into d. Suppose we have to construct the directed acyclic graph for this SDD, for this given SDD. So how we will construct? So one single difference is there between this syntax tree and directed acyclic graph. Here in whatever, suppose some expression is coming, this b minus c is coming more than one time here in this expression. So for syntax tree we will keep that one more than one times. Wherever, okay, suppose this one is coming 2 times, so we will use here 2 times. So but here in directed acyclic graph we can use this one time, and we can use. Okay, so here just see for this expression we can construct this parse tree, and syntax tree we can construct like this manner. Okay, so whatever operators are there, so that we have kept at internal nodes, and operands we have kept at leaf nodes. So for this one we can construct directed acyclic graph also. So here b minus c we have constructed one time here, and b minus c into d like this manner we can use, and this b minus c like a into b minus c like same way here we have used, and this a again no need to use, this one a plus this one we have used. Okay, a plus a into b minus, and this one is the directed acyclic graph for the expression a plus a into b minus c plus b minus c into d. Now here we will see postfix notation. Postfix notation is the useful form of intermediate code if the given language is expression. Postfix notation is a linear representation of a tree, syntax tree. In the postfix notation, any expression can be written unambiguously without parenthesis. Okay, suppose for example the ordinary way of writing the sum of x plus y is with operator in the middle, x plus y, like this one is the infix, but in postfix notation we replace the operator at the right end, and as we will write this one as xy plus. Okay, so here we can see like in postfix notation the operator follows the operands. Okay, this operator is following the operand. So this one is the postfix notation, and now here we can see 3 address code. So a statement involving no more than 3 references, 2 for operands and 1 for result, is known as 3 address statement. Okay, we use the term 3 address since instruction in our intermediate code consists of an elementary operation with 3 operands, each of which is often as address, often an address. Some of the 3 address operations have fewer than 3 addresses. We simply think of missing addresses as unused, or we ignore that one, ignore fields in the instruction. So here we can see common 3 address instructions form like assignment. This one is we can write like x equals to y operator z, or x equals to operator y. Okay, this one is binary and this one is unary. Okay, operator. Copy, suppose for this one we will write x equals to y. Unconditional jump, go to L. For conditional jumps, if x relational operator y, then we will go to L. Okay, if this condition is true, then we will go to L. Parameters, we will write param x. Function call, we will write call y equals to call p. Okay, if we are calling this p, and the value of we will keep in y. Index copy, y equals to x equals to yi, and here or we can say xi equals to y. Pointer assignment we will write like this manner, x equals to %y. Address of y we will keep in x, or here we can say x equals to pointer y, or this pointer x equals to y. Okay, so here we can see this 3 address code with the help of this example. Suppose we are having this expression a plus a into b minus c plus b minus c into d, and suppose we have to write the 3 address code for this for the given directed acyclic graph. Okay, so how we will write the 3 address code? So we can write the 3 address code for this one like b minus c we have given in some variable t1, and this t1 we are going to multiply with a. So here we can write a into t1. This one we have kept in t2, and a plus t2. This one we are adding with this one a plus t2. Here this one is becoming t3, and t1 this one already we have found this one into d, so t4, and t3 plus t4 whatever sum came, and here we are adding, so this one we are keeping in t5 variable. So this one is the 3 address code. So here we have used 3 references only, b, c and t1. Here also a, t1, t2, a, t2, t3, a, t1, t, t4. Okay, so like this manner. Suppose one more example also there, a equals to b into minus c. Here this one is unary operator, this one plus b into minus c. So t1 equals to minus c, this one we are keeping like this manner. So here we are keeping in t1 variable. After that this b into t1 we are keeping in t2 variable. Minus c again we are finding. This one again no need to find, but here this one we are not writing optimized 3 address code. Okay, But here if we are writing like this man, this one are also okay up to this time. So after that we can optimize this one also. So minus C, this one is T3, so B into T3, so here T4, T2 plus T4 we are keeping into T5 variable, and T5 we are keeping into A variable. So like this manner we can see here we have not used more than 3 references for writing this 3 address code. Now here we can see 3 address instruction can be implemented as objects or as records with fields for the operator and operands. Three such representations are called quadruples, triples and indirect triples. So for quadruples has 4 fields which we call as operator OP, argument 1, argument 2 and results 1 for result section. The OP field contains an internal code for the operator. For instance, 3 address instruction x equals to y plus z is represented by placing plus in OP, y in argument 1, z in argument 2, arg 2 and x in result for this one. Okay, suppose for this example we are having suppose a equals to b into minus c plus b into minus c. Okay, so how we will write this one? So this one is the 3 address code that we have already seen. So we can write the quadruples for this one like this manner. So here minus c, so minus operator, this one c first argument and t1 this one. These are the location or references here where we are keeping, okay, in memory. So this one is b into t1, b into t1 and this one we are keeping into t variable minus this operator c first argument and t3 is the result section. Like this manner b t3 and this asterisk is the operator and t4 we are variable we are keeping t2 t4 here argument 1 argument 2 and plus is the operator and we are keeping into t5 variable. This one is t5 we are keeping in a variable and this one is operator assignment operator. So like this manner we can write the quadruples. Okay, so like this another way also there for 3 address code how we can represent, that is triples. A triples has only 3 fields which we call OP, argument 1 and argument 2. Here result field is not there. So here this representation does not make use of extra temporary variables to represent a single operation. Instead, when a reference is to another triples value is needed. So here whatever reference is there, same here we will use for in this triple. Okay, while in quadruples you have seen we have kept here one more field, that is result. Okay, so we are not using that extra variable. So here this one we can write minus c and this one at this location we are keeping this t1. Okay, so here this t1 where we have kept at this location, so b into and this location we are keeping and this asterisk is the operator. After that this minus c, here this one we are keeping at this location. After that b into t3, this one we are using this 2 reference, okay, address. After that this t2 t4, so this t2 already we have found, here it is there 1 and 3 location and this one is plus we are doing, this one is operator. After that this t5 we are keeping, so here this one is assignment operator and in this we are keeping a, and what is that one, t5. So t5 is this 4. So like this manner we can write for triples. Same manner here one is indirect triples. So here it consists of a list of pointers to triples rather than a listing of triples themselves. Okay, with indirect triples, an optimizing compiler can move an instruction by reordering the instruction list without affecting the triples themselves. Suppose we are having this expression, how we can write? Same we have to write like triples, just here whatever references we have used, suppose later or in future if we want to update this 3 address code, or suppose we are changing the location in which variable we are keeping, so here we are just denoting this reference we are keeping at this location, so that wherever we have used this variable or location, so at all places means we can think like this one is present at this 35th at location. Okay, so like this manner here we will write whatever location or whatever references are there, we will keep here in separate list. Okay, so like this manner here this one is the indirect triples. Okay, so here we can see with the help of one example. This one is, suppose we are having one expression a plus minus b plus c. So we can write the syntax tree like this manner: a plus b minus c, b plus c, this one b plus c, and a plus, and this one is unary, so like this manner: a plus minus b plus c. This one is syntax tree. For quadruples we can write like this manner: b, c, and t1 result section, and plus is the operator. For this one, minus and t1, this we have already found this one, and this one is t2. Okay, we are keeping into t2 this one. After that, t1 plus t, this one we are keeping this one a plus, and this one is t2, this one we have found, and we are keeping into t3. So like this manner we can find the quadruples. So triples also like this manner. Just here we are removing this result field in this. So here we are keeping this same as it is. Just this one we have used. Here we will use the reference 0. Okay, and for this one a, t2 we are using this reference. Okay, so this one is the triples. And for indirect triples, just here in place of this one we can use another list, and we can write the references, so that if in future we are going to update the location or the variable, so with this we can think like wherever this location or this variable is present, so we can recognize from this place. Okay, so this one is the indirect triple for this given expression. So remaining topics we will see in next lecture. Thank you.